Okay, welcome. It's a great pleasure to have Carolyn Zhang as our speaker today. Carolyn got her PhD degree in physics from University of Chicago, I think in 2023, and now she's a postdoc at Harvard. I think everyone agrees that Carolyn is a superstar in the field, and her work is incredibly impressive in terms of both the breadth and the depth. So in terms of the breadth, Carolyn's work spans from generalized symmetries, topological phases, to quantum dynamics. And in terms of depth, basically in every of her paper, we can see some unique creative ideas and some very powerful techniques. Today, she's telling us about her most recent advancement. Please go ahead.
Yeah, thank you for the very kind introduction. I'll be talking about this recent posting with Rahul, Kurt, and Ruben. Um, and a lot of the talk will be thinking about a particular simple model, and there will be some technicalities, but hopefully there will be some ideas that can be more generally applicable in trial wave functions that can be more generally applicable when thinking about gapped and gapless states of matter. Um, let's see. So the basic question that we wanted to, oh, and please, yeah, interrupt at any time if there are questions. The basic question that we wanted to ask is what makes a state a gap ground state? So if you're handed a state psi, how do we know whether or not there exists a gapped parent Hamiltonian with some finite ground state degeneracy? Of course, any state can be a ground state of the zero Hamiltonian, so that's why we have this finite ground state degeneracy. There are some things that we can investigate about the state. First, we can ask, does it have area law entanglement? So if I take the entanglement entropy by tracing out a ball in d dimensions of radius r, there's a scale as r to the d minus 1 plus some order r to the d minus 2, where r is the radius of this ball. And this is a signature of being a gap ground state. Another signature of being a gap ground state is exponential decay of correlations. So we can ask if I take the correlation, these are operators, AX is an operator supported on region X, and BY is an operator supported on region Y. And we can ask if the correlations obey clustering. So this P omega is a projector onto the finite dimensional ground state subspace. And we can ask, does this guy decay exponentially with the distance between X and Y? So you can see if there's a unique ground state, this is just our usual familiar clustering of correlations. And this kind of clustering can be shown to, it has to happen if your Hamiltonian is gapped, but it may not be sufficient to prove that your Hamiltonian is gapped. These are all signatures that your state might look like a gap ground state, but in this work, we'll show that these conditions are not enough. So there are states that seem to obey these conditions, and yet there's an obstruction to finding a gapped parent Hamiltonian with finite ground state degeneracy. And usually when there's an obstruction to having a gap parent Hamiltonian, it's because of some anomaly, some property of the symmetries that prevent the possibility of a gap parent Hamiltonian. I don't know how to think about the states that we'll deal with, although there will be some reference to symmetries and one-form symmetries and spontaneous symmetry breaking at the end. So to put us on some concrete footing,
Excuse me.
yes.
Maybe for can we go back? Maybe it's useful to bring up the example of the W state.
Mm-hmm.
It's a state that satisfies both conditions. Suppose I take omega. I assume here by omega you mean the collection of all states.
So omega is the states in your ground state subspace.
Yeah. So here let's
So
assume omega contains only one state, which is the W state.
yes,
And
but
then it satisfies both conditions, but still somehow it cannot be the unique ground state of a gap of any local Hamiltonian.
yeah, so being part of a ground state subspace and being part of a unique gap ground state are different things. So from my understanding, the W state can be part of a degenerate ground state subspace also containing the zero state.
Yes.
Um,
So
yeah.
here the question is whether there's a gapped parent Hamiltonian for W state. I think the answer is no, right?
If there's some ground state degeneracy, then I don't see an obstruction.
In the paper that says W state cannot be the unique ground state of any local Hamiltonian, there's another statement saying such a Hamiltonian, besides having degenerate ground states, must also have gapless excitations.
I see. So that might be true. And in fact, there are going to be some superficial similarities between the W state and the state that I'll talk about today. Um, I was just aware of the part that the zero state also has to be in the ground state subspace.
Yeah, yeah, yeah.
So I was not aware that there also has to be an entire gapless spectrum.
Mhm.
So if that's the case, but something also peculiar about the W state is that if you there are correlations that are like 1 over L, right? So it's
Yeah.
not quite exponential in distance.
Uh,
Um,
uh,
but maybe if you put this p omega there, it is. So I'm not, yeah, I won't comment on the W state.
I mean, here, I think here when you make this statement, X and Y are two regions that are far away in a system which has a much larger size than distance between X and Y.
Yes.
Then in this case, when we consider W state, we need to consider a state where L, the length of the system, is very big. And then we consider X and Y, which are far away, but their distance is not as big as L.
Right, but there's always some scaling. So for example, you could take X and Y to be, say, like um, at positions L over 4 and 3L over 4. And then the scaling of their distance, you can take all these distances now to infinity, right?
Yeah.
Um, so the statement of this guy holding for gap ground states that you can prove is just about the distance between X and Y. So yeah, there are peculiarities about the W state. So I maybe, but I can comment about the W state at the end. There are, yeah, some similarities with the state I'll
Yeah,
talk about.
but let me just make sure. In this statement,
Yes.
do you assume you first take the thermodynamic limit?
Yeah, we will take the thermodynamic limit, but these can be operators that are, say, at L over 4 and 3L over 4, right?
Oh,
So the
I
thing
actually
that they
didn't.
need to be is like farther than a correlation length apart.
I actually didn't
Um,
know this before. I thought in this statement, we first take the thermodynamic limit, and then X and Y are just separated by some distance, which is not proportional to the total system size.
and the proof of this, I don't see a reason why you need to make that restriction
I see.
because the proof of this only relies on locality properties of the Hamiltonian. So it's just a statement of, oh, if X and Y are farther than the correlation length apart, then roughly speaking, there's some order 1 constants and your Hamiltonian's gap, then it should obey this condition.
Okay.
Yeah. Um, so yeah, I don't recall seeing any restriction on that. Okay. So the state that we'll be focused on, because we'll find some interesting structures about the state, is this model, psi beta. This is the toric code state on the square lattice. There are degrees of freedom living on the links. And this factor here just kind of suppresses the loops. So you can think of this as the all-up state. There are spin flips in loops. And this factor gives you an exponential suppression given by the length of the loops. And so you can see this is kind of like an Ising partition function, a classical Ising partition function in 2D, also seen in various contexts, which I will just mention shortly. And there's a simple parent Hamiltonian we can write down for this state. This is one example of a local parent Hamiltonian we can write down for this state. You can see that it's a frustration-free Hamiltonian because these two terms annihilate this state, and it's positive semi-definite. And this AV term commutes with both of these terms, and this state also minimizes the AV term. So this is a frustration-free parent Hamiltonian for this state. And on periodic boundary conditions, this Hamiltonian has an exact fourfold ground state degeneracy. There may be other low-lying states that become exponentially close. That doesn't seem likely. Seems like there's a fourfold ground state degeneracy. And you can ask, is this Hamiltonian gapped? And does a parent Hamiltonian for the state need to be gapped? So this state looks very simple and is especially simple in certain limits. So as beta goes to infinity, you can see that this is just going to give you toric code. The Hamiltonian on the previous slide reduces to the toric code Hamiltonian with a slight modification by a small field. And we know that the toric code is stable to perturbations, and so this should remain in the toric code phase. As beta goes to infinity, we recover a product state because this guy just projects you into the all-up state. And it's actually known that there is a toric code phase up to beta C. Beta C is related to the critical inverse temperature for the 2D classicalizing model. And it's not too hard to see that this whole phase up to beta C is in the toric code phase. It's a gap ground state. The Hamiltonian is gapped. But the surprising thing that we'll see is that for beta between beta C and infinity, the Hamiltonian is actually 1 over L cubed gapless, and this state kind of forbids a gapped parent Hamiltonian that is local. Right, so this state has been studied in many different contexts because it's simple and there are things that you can compute exactly about it. It's known as a Roxor-Kivelson type state because it encodes a 2D classical partition function in a quantum state. Its critical properties at beta C were investigated in under the name of conformal quantum critical points in various papers, including this one. It has an exact tensor network description as a PEPS with bond dimension 2, studied in this paper. Its entanglement entropy and topological entanglement entropy was computed exactly in this paper. So it was shown to be the usual log 2 for betas less than beta C, and 0 for betas greater than beta C. And its peculiar kind of loop operators were studied in this paper and kind of were part of the inspiration for this project. And it comes naturally in certain contexts. So it naturally arises in the choice state of decoherent topological orders. And there's also a relation that's not so obvious between parent Hamiltonians for this state and classical kind of Markov processes that take you to classical Ising Gibbs state called Glauber dynamics. And so this state is also related to studies of Glauber dynamics. And there were already hints back in this very old paper that parent Hamiltonians for the state for betas greater than beta C might be gapless. And there are arguments in this paper if you interpret the results in the correct way. So one of the things we'll show is that the parent Hamiltonian that I showed earlier is gapless for betas greater than beta C, despite the fact that it has 0 entanglement, topological entanglement entropy, and this entanglement entropy behaves as a strict area law. And furthermore, if this Hamiltonian is frustration free, which it is, we'll show that the finite size gap is upper bounded by 1 over L cubed on a torus. And we'll give a construction of the low energy states. And these states have a peculiar nature of being very non-locally generated. So they don't really describe quasi-particle excitations on top of your ground state. These two asterisks are for the first asterisk is we'll focus on exact ground state degeneracy for the purpose of this talk. And I can mention at the end how we expect this to generalize to finite splitting. So we'll assume for the purpose of this talk that the Hamiltonian has an exact fourfold ground state degeneracy, which it does, and no other states, which is very aligned with numerical results. And we'll also require some mild assumptions on families of gap Hamiltonians, which I will mention shortly. So you can keep in mind this very simple state and the the plan for the rest of the talk is I'll first mention the peculiar properties of the state, why we were suspicious of it when we first saw it. And then we'll present two theorems. So the first theorem says that any local parent Hamiltonian of the state for beta is greater than beta c must be gapless or extensively degenerate. And the second theorem, which is more of a physicist theorem because there's some assumptions that go into it, is that any frustration-free one-form symmetric parent Hamiltonian, for example, the one that I flashed earlier, you can see that it commutes with product of z on all loops, must have a finite size gap that's upper bounded by 1 over L cubed on periodic boundary conditions. So this is like the states above the fourfold ground state degeneracy. Okay, so after I kind of give the sketch of the proofs of those two theorems, I'll mention the relation to one-form spontaneous symmetry breaking and non-modular tensor categories, and also some further applications, and some directions for future work. Okay, the basis of theorem 1 will be using the Lee-Robinson bounds, and then theorem 2 will will use a variational wave function to get kind of a better idea of what these low energy states are. Okay, so why would you be suspicious of this simple looking state? So if you look at this phase diagram from Hastings and One from back in 2005 about the stability of topological order, they have this phase diagram for the torque code model with X and Z fields. And so there's the usual deconfined torque code phase in the middle. Along these axes, you have an exact one-form symmetry. And then outside of this phase is a confined or Higgs phase. And you can see that the axis we'll focus on is just along, say, this axis. So along this axis, you have exact one-form symmetry. So that's this V of gamma hat. So this is along any kind of closed loop on a dual lattice is equal to 1, even for kind of both contractible and non-contractible loops. Along this line, you also have, as they write here, perimeter law for the Wilson operator. So this line operator decays as the length of the loop. And then you also have exponential decay of an open string. So if you have an open string, you take the expectation value. So the alpha will always refer to an open string. It decays as the distance between the endpoints of the open string. These are typical kind of properties that you would expect along this line here. On the other hand, in the confined phase, you expect, well, you still have the one-form symmetry, and the difference is that now the charged loop operator, so these braid non-trivially, the charged loop operator decays as the area enclosed by the loop, and the open string has order 1 expectation value. It doesn't go to 0 as you take the endpoints far away. The intuition behind these two behaviors is that the deconfined phase can be identified with the Ising paramagnet, and in this phase, the disorder parameter decays as the perimeter. So the disorder parameter is the expectation value of the symmetry operator restricted to a patch. And so you expect that in the paramagnet phase, there's a way to kind of dress this patch so that you have expectation value 1. And so without the dressing, this guy decays as the perimeter. And the order parameter decays exponentially. And the reason why you would expect these behaviors in the confined phase is because now the order parameter is order 1, and the disorder parameter decays as you would expect decays as the area. And in this recent work, we proved this fact in the vicinity of the Ising fixed point. But it hasn't really been proven for the entire phase. But it's kind of intuitively true. Okay, so the problem with the state for beta is greater than minus beta times the length of the loops in that configuration. For beta is less than beta c, this is perfectly aligned with the properties of the deconfined phase. And for beta is greater than beta c, you still have a one-form symmetry, which is the product of z. You can see that this guy has expectation value 1 in this state. this product of X loop decays as the length of the loop, so it looks like it's in the deconfined phase. However, the open string of product of Z has an order 1 expectation value. And this comes from the fact that for beta is greater than beta C, this is like a 2D classical Ising partition function, and the order parameter becomes order 1. And the order parameter once can be identified with this open string. And so from certain correlators, it looks like it's in the deconfined phase. And from other correlation functions, it looks in the confined phase. And so it didn't really fit anywhere in the phase diagram that was drawn previously. So you might suspect that it might not belong in any gap phase, despite the fact that it doesn't have any obvious obstructions to being a gap-bound state. Okay, so the first theorem that we will show is that under certain correlations, so these 1, 2, and 3, if a state obeys these three, then it can't be a ground state of a local Hamiltonian with a finite ground state degeneracy. So this uses two string operators, W and V. In this case, in the previous example, we considered Z2. And they braid non-trivially. So that means that if the loops intersect, then and pulling them apart gives you a phase. And these three properties are related to what I just mentioned. So the first property is the one-form symmetry. So the product of Z, expectation value product of Z is equal to 1. The second property is the perimeter law for contractible loops and the long-range order of the open string. And then the third property is basically saying that the state isn't like a superposition of the toric code state in an up state. So if you do like this kind of superposition, you could kind of make it look both trivial and topologically ordered. But you can show that this state isn't the state that I wrote earlier for beta is greater than beta C isn't of this form. And there's a proof in the paper that if your state obeys this kind of short-range correlation of the open string, then if you take this open string, you act it on your state, and you project back into the ground state space, you get something proportional to the state. So basically, this open string doesn't transition you between different ground states in your ground state subspace. So these are all conditions that are pretty physical and obeyed by the state of interest that I just showed. And we'll show that it can't be a gap ground state of a local Hamiltonian, and local meaning, roughly speaking, it means that the local terms decay with the diameter. So you have a local term, and its norm is very suppressed if it acts on a bunch of qubits. One thing that we will use, which is a little bit suspicious, but I don't know if there's a better proof method, is that we'll have to assume that things like the gap are independent of finite aspect ratio. So if you take both Lx and Ly to go to infinity, but you keep their aspect ratio to be finite but fixed, then the gap doesn't change. And the intuition is that the gap can only really change if you kind of change the dimensionality of the system. And that happens when you take the aspect ratio to be 0 or infinite in the thermodynamic limit. But if you take a finite aspect ratio, then things like gap shouldn't really care about what particular value that aspect ratio is once you take both Lx and Ly to infinity. Okay, so this is the first theorem. And the second one is about frustration-free parent Hamiltonians. So for this theorem, it's convenient to work with the dual kind of Ising model compared to the toric code one that I mentioned earlier. Participate has enabled translation. Okay. And for beta is greater than the beta C in dimension D, we can show that the gap of any frustration-free Hamiltonian, parent Hamiltonian of this kind of Ising-like state on periodic boundary conditions is upper bounded by order 1 over L to the D plus 1, where L is the linear system size. And furthermore, we'll show that these excited states kind of take this loop wave form. So we'll show that there's a state that sort of looks like this loop wave that has very small energy and very small overlap with the ground state. And so because it takes this loop waveform, it can't really be described by creating quasi-particles on top of the ground state. Um, so in particular for d equals 2, which we're primarily interested in, it would be 1 over L cubed. Okay, before we kind of jump into the details of how to go about these proofs and variational wave functions, I'll just flash up some numerical evidence for the results that I just mentioned. So on L by L torus, you can see that the low-lying excited state looks like the gap closes as 1 over L cubed for a not too horrendously large or small. And so this gives evidence that this is for the frustration-free Hamiltonian that I just mentioned. This gives evidence that it seems to be converging as you increase the bond dimension to this 1 over L cubed. And then this is a ZZ correlator in space. So you can see that the spins like to be anti-aligned on opposite sides of the torus, and you have these kind of straight domain wells that are reminiscent of this kind of state that I wrote down here. So of course, we haven't fully converged everything, but this gives some evidence to support the properties that I mentioned earlier. Okay, so the sketch of the proof of theorem 1 is as follows. Theorem 1 really just uses the peculiar correlations that I mentioned earlier and one additional ingredient, which is clustering of correlations. So as was proved by people including Hastings, Nachtergaele, and Sims, if you have a gapped parent Hamiltonian, then correlations in the ground state subspace cluster in this way. And so this holds, you can kind of prove this whenever the Hamiltonian has the order 1 gap. And again, this p omega is a projection into the ground state subspace. There's usually also a term that is proportional to the splitting, but because we've assumed that there's an exact degeneracy, we don't need to worry about that term. And the basic idea is that we'll compute this quantity in 2 different ways. A lot of the ways that people use to prove things like long-range order are obtained by computing loop correlations on a torus, and we'll do something similar. So we'll compute it in 2 different ways, and then we'll find a contradiction for various aspect ratios. So for various finite aspect ratios. This looks like a rather strange correlation. So this W of gamma L is this blue string here, is decays with the parameter. This V of alpha L is this open string here. If you linked it together with V right, then it would have expectation value 1 in the state. And then W gamma R is this string over here that also is the one that decays with the perimeter for any contractible loop. So we'll compute this in 2 different ways. The first way that we can compute this kind of correlation function is by applying clustering. So you can cluster whenever you have 2 operators that are supported far apart. So in this case, we'll cluster the left operators from the right operators at the cost of some very small error. And then we use the non-trivial braiding relations between this V left and W left to get this phase that's non-trivial. And then there's we can change this V left to V right because we can use the fact that there's a one-form symmetry, so we can always exchange V left with V right when it's acting on the state. And then we can cluster again and then revert this back to V left. So this is 3 steps. We use the one-form symmetry, we use clustering, and then we use no transitions. This is slightly different from the usual clustering. It's kind of a sequential clustering, but the proof of that is in the paper, and you can sort of believe that you can sequentially cluster. And
Okay. What does no transitions mean?
oh yeah, so the no transitions was the condition that I mentioned earlier, that this p omega v alpha on the ground state is proportional to the ground state. So this open string doesn't take you between the different ground states.
I see.
And so you can check that that is satisfied in this psi beta state. And this, remember, that came from the fact that psi beta is not like a superposition of a torque code state plus the all up state. So it came from, is not like a first order transition between torque code and trivial. You can prove that those things are kind of the same. Okay. Because if it was such a state, then if it was such a first order transition, then these open strings, 1, B alpha 2, these would not cluster. Alpha 2 would not go to 1, 0. Okay, so the second method is that we first pull this W V alpha left through W gamma right. And that's just because they have different disjoint supports, so you can just pull through. And then we can convert this V alpha left into V alpha right. So it's using the disjoint support to commute through and then the one-form symmetry. And then we can use clustering because we have a bunch of operators on the right and an operator on the left. And then we can, again, take this one to an alpha left, cluster again, and then so this use one-form symmetry, clusters, and no transitions again. So these are the 3 different steps for each method, and now all we have to do is equate this guy with this guy. And the important thing is that all of these errors are exponentially suppressed in LX. So if we equate those two quantities that we just computed, we see that this is actually the same thing as this guy here. So we can pull this over to the right-hand side, pull this error over to the left-hand side, and we get this quantity. The important thing is this one is order 1. And this guy you can show from the perimeter law is exponentially small in this Ly. And so then what you end up getting is that something that's exponentially small in Ly is equal to something that's exponentially small in Lx. But this can always be, this kind of inequality can always be violated by choosing an appropriate alpha over mu. And these alpha and mu's are all order 1. So you can always choose a finite aspect ratio to get a contradiction here. And then we can use what we discussed earlier, that kind of the gap shouldn't, it would be very weird to have a Hamiltonian that's translation invariant and is gapless at a certain aspect ratio, finite aspect ratio, and gapped at a slightly different finite aspect ratio. And you can put more kind of meat on that claim, but if we just take that as a given, then this gives you a contradiction and says that everything kind of decays exponentially, but somehow doesn't decay quickly enough for this to be a gap ground state. You either had to kind of have this one decay exponentially or have this one decay with the area
So how
for
important
this.
is translation symmetry?
You don't need to have translation symmetry, but there needs to be some way to take a thermodynamic limit. And that's not completely obvious if you just have some random system with random couplings.
Mhm. And it seems you mentioned translation symmetry makes us feel more comfortable if we assume the gap doesn't depend on the aspect ratio.
Yeah, but I don't think it's so important actually. Like you could add some defects so that you don't break, you don't have like a strict translation symmetry, but it would still work. Um, and the reason is if you have a gap, then as long as Lx and Ly both go to infinity and their aspect ratio is finite, then you can't really have one Lx be shorter than the correlation length or Ly shorter than the correlation length. So the gap should remain open and be independent of this finite aspect ratio until this goes to 0 or infinity because either Lx or Ly has become smaller than the correlation length.
Mhm.
But
Uh,
that doesn't like use that just get you kind of have some intuition from translation symmetry, but that's kind of an assumption that we're taking that likely holds even if you don't have a fully translation symmetric system.
mhm. Can you go one slide back?
Yeah,
I think I have a very simple question.
I don't, not sure how to go back. Um, Oops. Okay.
So in the second step of clustering, for example, in the last equation, W gamma L dagger P W gamma R. So I guess how how do you use clustering here?
Yeah, so we don't use the clustering that is in the Hastings paper. We use a slight generalization of the clustering. So you can show that now we're going to change this to a gamma left, which we can because we can exchange left and right if it acts on the state, right? Because it's an eigenstate of left times right. And then we can use that gamma right is very far supported from alpha left to insert another p in here. So this is goes beyond the usual statement of clustering and requires a bit more work, which we prove in the paper.
Uh-huh.
So this is what I mean by sequential clustering. You have a p omega here, and then you can also insert another p omega between these two operators because gamma left is supported from far from alpha left.
Mhm.
Yeah, alpha left is like here, and the gamma right is like here.
And you mentioned that you need to use the Lieb-Robinson bond. Is this where it's used?
Yeah, because whenever you prove clustering, that's using Lieb-Robinson bounds.
Yeah.
If you look at the proof for clustering, it uses, um, yeah, Lieb-Robinson bounds plays a crucial role there.
Yeah. Okay. Thanks.
Hi, Caroline. A quick
Yeah,
question.
yeah,
I'm probably taking a wild guess here, but if I look at this torus and think of it as a thin cylinder,
yes.
does this have anything to do with the fact that order parameter and disorder parameter cannot be order one in the at the same time? You know, I'm imagining something. I mean, this is close enough to Ising. And the V guy the alpha L looks like a disorder parameter, and then the W could be, in the thin cylinder limit, look like an order parameter.
Yeah, so in 1D, um, it's kind of saying that they're both order one, but we didn't really want to take
Hmm.
a 1D limit because then
Hmm.
one of those sides are smaller than correlation length, so it's not really the same as talking about a 2D system.
Hmm.
Um,
I see,
and you
but
can
in
imagine
spirit, it's
like,
similar. It's just a different limit that you have to take. So I suppose there are technicality there.
right, but you can imagine like a 2D system that once the edges can talk to each other enough, it becomes gapless as you bring it to 1D, right?
Hmm.
So that's why we kind of didn't want to just say, oh, if we take a quasi 1D system, then there's something wrong about the
Hmm.
state.
Okay,
Yeah.
thanks.
Um, okay. Thanks for the questions. Um, okay, so comments about this theorem. First, it doesn't rely on the Hamiltonian having one-form symmetry. And second, it does rely on things like gap, Lieb-Robinson velocity being invariant as Lx and Ly goes to infinity for a finite aspect ratio, which you can show in certain cases happens. And a immediate corollary is that if we take the kind of dual Ising model, then any Z2 symmetric parent Hamiltonian is gapless for beta is greater than beta C. And so, well, strictly speaking, we didn't get this how gapless it is. This shows that at least this region, it seems like the subtle kind of correlations prevents you from having the usual gapped system. Um, okay. The second theorem is about
Hi,
frustration.
excuse me. I have a question.
Yeah.
Could you please go back to the previous slide? According to proof, I want to make sure if I'm understanding correctly. So according to the proof, I think there can be some specific and some very specific aspect ratio that does not violate the equality, right?
So it's like for Lx over Ly smaller than some order one constant, then
Um,
it doesn't violate. But for if it's greater than some order one constant, it does.
then for these specific ratios, does it mean that the system can behave very differently from from other aspect ratios? I mean, for example, for CFT, if you have different ratio of orbitals, the system can behave very different. Then is this the
Yeah.
case here?
So we're assuming that if it's a gapped parent Hamiltonian, then the gap remains order 1 as you take Lx and Ly goes to infinity for finite aspect ratio. And this is because as you take Lx and Ly to go to infinity for a finite aspect ratio, there's no way for either length to be smaller than the correlation length. So this is kind of specifically for gapped systems where you don't expect those kinds of aspect ratios to come into play.
I see. Thank you.
So then because it is violated for some large but order 1 Lx over Ly, then it seems like it should also be gapless for Lx over Ly smaller than that critical order 1 sort of aspect ratio.
I see. Thank you.
Thank you. Okay. And the second theorem is about frustration-free Hamiltonian. So for this purpose, it's convenient to work in the Ising picture. And so again, we have a state that is a 2D classical Ising partition function. And if we take the beta greater than beta c for whatever dimension that you're in, we'll show that the gap, the finite size gap of this frustration-free Hamiltonian has to be upper bounded by something like 1 over L to d plus 1. And by frustration-free, all I mean is that it's a sum of local terms. Each of these are exponentially decaying or super polynomial decaying in the diameter, and they each annihilate the state. So for example, we can construct many kind of frustration-free Hamiltonians. One of them is obtained by gauging the one for toric code that I mentioned earlier. Gauging the one form symmetry. And a corollary is that any Z2 symmetric parent Hamiltonian has to have a gapless Z2 even sector. So this doesn't actually require frustration-free. And it comes from a mapping between gapped Hamiltonians and gap frustration-free Hamiltonians. So you can show that any gapped local Hamiltonian can be written as a gapped frustration-free quasi-local Hamiltonian under certain assumptions. And I can go more into this. It's also in one of the lemmas in our paper. And so this is really gapless because it's not just the splitting between the even and odd ground states. In the even sector, there's a gapless spectrum. Okay, so the way that we'll prove this is by constructing trial wave functions that have very low energy. To construct these trial wave functions, it's convenient to write the state as, again, a superposition of domain walls with weights on each domain wall state. And this weight is just this Boltzmann factor for the domain wall state. So you can think of this set of domain walls, as I wrote here, just a bunch of up and then flip down on various domains. And each of these states come with their appropriate Boltzmann weight. So it will be convenient to use this basis of domain wall states. And so we'll define a state that is not just this Boltzmann weight, but also has a theta function. So theta is a function of the domain wall configurations. And we will show that there's an appropriate choice of theta such that its overlap with this ground state is very small. It's exponentially small in the linear system size. And the expectation value of the Hamiltonian in this state is order 1 over L cubed. So because it's orthogonal to the ground state in the thermodynamic limit, and it has very low energy, that means that there must be other states that are very low energy. And even though we will construct just one state, it's not too hard to show that there should be an entire family of states. So there should be an extensive number of states that are all orthogonal to each other and have 1 over poly L energy. But I'll just focus on one such state. Okay, so how do we construct these low energy states? And let me just reiterate that we can parameterize this state using this Boltzmann weight and this theta function on the domain wall configurations. And the key ideas is that if you have a local Hamiltonian, then from the perspective of each local Hamiltonian term, it really only cares if your state locally looks like the ground state. And so it will be very small. It will have small expectation value if your state locally looks like the ground state. That will be very useful. Another thing that will be very useful is that if you have a local Hamiltonian, then it can only transition you between two different domain wall states that are rather close in Hamming distance. So they're only differing by order 1 in Hamming distance, and that just comes from locality of the Hamiltonian. If you use some algebra using the fact that this is frustration-free, one can show that the expectation value of a Hamiltonian term in this trial wave function is roughly given by the sum over the differences of these theta functions between states that are connected by hx. And then there's also this Boltzmann factor out here. So this delta function basically restricts the C prime such that these two are configurations that are connected by this local Hamiltonian term. So then the goal that you need to, the kind of guiding feature is that you need to find a function theta of the domain wall configurations that varies very slowly with Hamming distance, because we know that these differ very small by Hamming distance. So then if this theta function varies very slowly with Hamming distance, then this guy will be very small. And if it has configurations where it doesn't very slowly, then this factor must be very small. So those are the two guiding features that we need to take care of. So there are two steps to constructing these low energy wave functions. The first step is that we first restrict to domain wall configurations with a large domain wrapping the cycle. And the reason why we do this is it's very hard for a local term to detect whether you have a large domain wall wrapping the cycle or not. This is because the number of windings is a non-local quantity. So any local Hamiltonian term that looks within the vicinity of some sites will not be able to tell whether you have a domain wall wrapping the cycle or not. So locally, it kind of looks like the ground state. And yet it has exponentially small overlap with the ground state because for large beta, the ground state is dominated by small domain wall configurations, meaning it does not like to have these large domain walls. These are very, very costly in the ground state. So you can show that this has very small overlap with the ground state. And yet is locally kind of hard to distinguish from the ground state. And then we can, now that we're in this kind of single domain wrapping cycle, we can define a center of mass, a delta x, that is a center of mass difference between the two domains. So this is going to, you can, pictorially see what I mean by the center of mass difference between the two domains here. One thing that's important is that the expectation value of contractible loops only depends on the perimeter. So this kind of domain wall configuration is just as likely as if you kind of shift the right domain wall a bit and shift the left domain wall a bit, because that doesn't increase the length of the domain wall. Okay, so now that we restricted to this kind of winding sector, the second step is we're going to choose a theta function that is very slowly on the Hamming distance. And so we're going to slowly ramp up this theta function such that it starts ramping up from 0 when the center mass difference between the two domain walls are Lx over 4, and eventually peaks at 1 when the center mass difference between the domain walls are maximal. So you really have a huge domain wrapping half of your system. And we need to choose this to be a slow function, so we choose a linear ramp. So typically what will happen is a local Hamiltonian term will just kind of slightly perturb one of these domain walls. And so it will only change the center of mass by something like 1 over Lx. And then if you look at this quantity, which is the difference in theta for this guy and theta for this guy, it'll be like 1 over Lx Ly, because you divide by an extra Lx here. Okay, so that was the point, is for most kind of configurations, this quantity is really, really small. It's order 1 over Lx Ly. You square it, so it's 1 over Lx Ly squared. The only possible out is if you have something like this kind of kissing point. So you have two very, very far separated domain walls, and they meet they wiggle to each other and meet so that when you act with a local Hamiltonian term here, it can take you out of this sector. So because it can kind of connect these in a way that you get out of the sector. It reconnects this so that you no longer have a winding domain. But these you can show are very, very suppressed. So they're exponentially suppressed in this distance compared to the other kinds of domain wall configurations. And so you can show that the error from this is very small. So kind of the point is that there's a vanishing, this kind of plateau between Lx equals 0, delta x equals 0, and delta x is Lx over 4, suppresses the contributions from these kissing points, and then the slow ramp reduces this difference in theta functions. Okay, so those were the two ingredients that went into play, and then with some simple algebra, you can show that you can show that the expectation value of the Hamiltonian should be upper bounded by 1 over Lx squared Ly. The extra factor of 1 over Lx comes from the fact that if you have a local Hamiltonian term, there's only a probability of like 1 over Lx that it actually even touches your domain wall at all. And if it isn't near your big domain wall, then it doesn't contribute to the energy.
So
Okay,
is it possible to generalize this statement to fluctuation-free Hamiltonians that have polar decaying interaction?
That's not obvious to me then, because there are certain things like the Hamming distance that you can connect different configurations. But so there might be like a critical power, but I would have to be more careful with that because, well, first you need to show that this guy remains small usually, and then second you need to show that these kind of kissing point configurations still remain suppressed. So there might be a critical power, but I haven't thought rigorously about that.
Thanks.
Yeah. This sort of looks like an LSM type of state because there's a slow ramp of some parameter, but I don't know how to rigorously make a connection to like large gauge transformations associated with asymmetry. But in any case, the picture of the wave function looks sort of something like this. And if you just naively did a sum over straight domain walls, you would definitely not have a state with low energy. You really needed all of these fluctuations so that from the perspective of a local Hamiltonian term, it looks like you're in the ground state. Okay, I'll just mention some ways to understand this from the perspective of one-form spontaneous symmetry breaking. It's in the literature, it's often said that the spontaneous symmetry breaking of a one-form symmetry is marked by an exact loop operator and a charged operator that's kind of long range. So it decays as the perimeter instead of with the area. And the idea is that, okay, so if we take this as our definition of one-form spontaneous symmetry breaking, then it seems like what we have is a spontaneous symmetry breaking of a non-modular one-form symmetry. So usually when we have this behavior, there's a dressing of this loop so that you also get another exact one-form symmetry that's also spontaneously broken. But for betas greater than beta c, we don't believe that such a dressing exists. Even though this decays with the perimeter, we believe that there's no dressing. And the reason is because the topological entanglement entropy is 0. So if there was such a dressing, it would not be 0 because there's a lower bound on TEE. Once you have two line operators that break non-trivially and have expectation value 1. So from the perspective of one-form spontaneous symmetry breaking, it looks like it is spontaneous symmetry breaking of a non-modular category. And this V gamma hat can usually be identified with the vacuum if you have just like in the confined phase. But here we have a fourfold ground state degeneracy, and this operator actually acts non-trivial in this ground state subspace on the torus. And so it can't be identified with vacuum. And then the common lore says that if you have a non-modular tensor category, and here is just one in a boson, then it's not the ground state of a local gapped Hamiltonian. I don't see it really proven rigorously in the literature, but this gives an example where we do find this non-modular category, tensor category, this one and boson, and it doesn't seem to have a gap parent Hamiltonian. But it would be interesting to kind of study this lore on more rigorous footing.
I have a quick question. So,
Yes.
you made a comment that the dressing doesn't exist, but one can always do something probably pretty dumb, but I could just put a factor of e to the mu uh,
Yes.
to the length of, the loop on the
Yeah.
left-hand side to compensate that, and that obviously isn't a good thing to do. But what exactly is bad, actually, if I do that kind of pretty naive dressing?
Yeah, so then it's not unitary anymore, and the clustering bounds from Lieb-Robinson always has operator norms in it. So you'll find that the factor that you multiplied will cancel out with the factor from the operator norm. And so then you won't actually fix any contradiction that uh, from the proof that we had. Was that your question, or?
Well, I guess I think the issue still exists, but probably I was asking a question like, what is supposed to be, the W cannot be any random looking thing, because if
Yeah.
you allow me to do that, then I can just multiply any factor so that I can compensate the exponential decay and make it one. And if I don't have
Uh-huh.
access to microscopics, I would not know if W expectation equal to one means the bad kind of aerial. Is it really one, or is it like what you said, that has an e to the minus mu to the length, and
Uh-huh. Well,
fixing that
W
actually
has a
doesn't
certain
fix other problem?
Yeah, so W has certain properties, right? Like it has certain fusion properties. It's a ZN operator. So those would definitely change if you just multiply it with
Mm,
uh,
right, that's
non-unitary
true.
factors. So it wouldn't be a Z2 operator anymore. Um,
Mhm.
yeah, so this is saying that there's a Z2 one line operator, B, and the vacuum operator. So that kind of forms your
Mhm.
non-modular category. Does that answer your
Mhm.
question?
I think so. Yeah, thanks.
Okay. Um, Okay, so there are some applications, some more obvious and some maybe less obvious depending on what kind of audience you are. One application is to Markov processes. I accidentally capitalized this M instead of this M, but um, so Markov processes are ways to simulate classical, like say classical Ising model in 2D. And it basically says if I have a set of configurations and their probabilities, then I can get another set of configurations with their probabilities by acting with a transition matrix. That says if I have this configuration, I have probability of X, Y, Z of going to other configurations. And there's a well-known mapping between frustration-free Hamiltonians with this sort of partition function ground state and classical Markov processes like Glauber dynamics and Metropolis. Um, And so you can show that actually the spectrum of the Hamiltonian is the same as related to the spectrum of the transition matrix for Glauber dynamics and these classical Markov processes. And it was actually kind of suggested or proposed in this paper that did a lot of numerics with Glauber dynamics that on the torus, the gap might go as like 1 over L cubed. So this gives a nice confirmation of that on more rigorous footing. And also, uh, there's more I can say about Glauber dynamics in higher dimensions, but I'll just leave it at that for now. Um, Another application is to mix states. So it's not hard to take a sum of short range entangled states, and it's not strictly speaking, doesn't have a short range entangled purification. By error threshold, I just mean if you put this torque code pure state through incoherent error channel like Z or X noise, then this has been studied in many context papers initiated by Yimu and Reihua and Ehud and Ashvin, where you can study the sensing matrix and there's a torque code phase below PC and a trivial phase above PC. And so in kind of work in progress with Rahul, Kurt, and Ruben, we are applying it to these kind of decoherent states. The reason why you can still call this a trivial phase is the short story is that even though there's no short-range entangled purification, strictly speaking, there's a density matrix that is epsilon close to this. We believe there's a density matrix that's epsilon close to this row that does have a short-range entangled purification. So whenever you're doing things like pest recovery, there's an epsilon error, and this is absorbed in the epsilon error. And so whenever you're talking with states, maybe you want to also include, and this epsilon can be taken to 0 in the thermodynamic limit. I can say more about that as well if there are questions. Okay, so some remaining questions is, there were some assumptions about the behavior of the gap with aspect ratio and things like that. These were assumptions that are reasonable, and maybe there are ways to make them more rigorous. And we showed kind of locally gapless modes that we showed non-locally gapless modes. So they aren't created from the ground state with the sum of local operators, but it's likely that they're also locally gapless modes, so actual quasi-particle modes. And there's reasons why you might suspect that from Markov dynamics, why they're locally gapless modes in 2 dimensions. And so, yeah, but we don't know how to construct them. So that's something that we haven't really figured out. So what you can imagine is that there's these 1 over L cube non-locally gapless modes that are not quasi-particle-like. And then there are maybe quasi-particle-like modes that are maybe something like 1 over L squared. So they lie on top of the very low-lying states. Yeah, because these gapless states are very non-local, it's more non-trivial thinking about what happens to them when you go on different topologies and different boundary conditions. So the proof that I mentioned, you can go on any genus greater than 1. The frustration-free states should also work with any genus greater than 1. But similar to the locally gapless modes, we don't have a clear, rigorous idea of what happens on a sphere. There's also a lot of work on other deformed wave functions because you can do a lot of nice analytic results on them. So it'd be interesting to understand the generality of these kinds of states. One interesting thing is Hamiltonian perturbations. So there was a paper in 2011 that was studying these conformal quantum critical points, and they found that, so you can think of this x-axis as beta, and this is our 2D classical Ising critical point, and all these points are actually 2 plus 1D quantum Ising. So what you would expect is that this is a deconfined phase in Tor code, and this is a confined phase, and this is some Hamiltonian perturbation. So it seems like any perturbation above, this is our gapless region, and then any perturbation above immediately takes you to some gapped phase. But it would be interesting to see what goes in the negative h-axis, because you might ask, is this gapless line some transition between this gapped phase and something else? And then this, also brings to light what are the necessary and sufficient conditions that one might want for, say, ground stability, gapped ground stability, and do the non-locally gapless modes that we presented, can they kind of provide ansatz when one is looking for low energy states in other contexts? So the thing that we really use are these kind of different sectors, these winding sectors, and there's a bottleneck getting between these sectors. So that's the kind of intuition that might provide help in constructing low energy states in other contexts as well. Okay, that is all I have for today. Thank you for listening.
Thank you, Carolyn, for the very interesting talk. Any other questions? I have a question. You mentioned for, I don't remember what exactly you mentioned, but you mentioned something like for gapped Hamiltonian, there's a way to write it as a frustration-free Hamiltonian, something like that.
Yes.
Well, what's the statement?
Yeah, so the statement is if I have let me try to change the color so it's not yellow. Okay, so if I have a Hamiltonian H, and it's gapped, I can write it as, if there's a unique ground state, I can write it as sum of H tilde x, where these H tildes each annihilate the ground state. There's a construction. And this construction also works if you have a degenerate ground. So that construction is no, it's not too hard to show. If it will take me like 2 minutes to show if you're interested, maybe less than 2 minutes. There's so something that's maybe not as much appreciated in the literature is that this construction from gapped Hamiltonian to gapped frustration-free Hamiltonian also works if the only ground state degeneracy comes from states in different symmetry sectors. And this Hamiltonian doesn't, the Hamiltonian terms are symmetric, so they don't connect states in different ground states in your degenerate subspace. So for example, if you have an Ising model that has a twofold ground state degeneracy, where the states lie in different symmetry sectors, and your Hamiltonian is Ising symmetric, then you can also use this construction to go from a gapped, oops, I have it, to go from a gapped Hamiltonian, oh my gosh, to go from a gapped Hamiltonian to gap frustration-free Hamiltonian. I can run through this exact mapping if you're interested.
But this is in your paper.
Sorry?
This is in your paper.
Yeah, it's in the last appendix of the paper. How to get from this to this. And this H tilde x's are super polynomially localized.
I see.
Yeah.
How is the condition of gap used?
Yeah, the condition of gap is because so this construction uses a filter function. And the filter function, so yeah, you basically need a function whose Fourier transform for omega. Oh, that doesn't look good. Okay. Fourier transform for epsilon is equal to 0 for epsilon greater than the gap. And then its Fourier transform is 1 when this is 0. And so if you take this gap to be one, like vanishing in the system size, then you can't find such a function that is smooth enough, basically. And so then the W itself won't be local, won't be quickly decaying. So that's why you need a gap that's order 1 for this construction to work.
A related question, maybe not too related, is suppose I have a local Hamiltonian. I just want to check whether it's frustration free. By frustration free, I require this H tilde to be local instead of having some decaying form. Is there a general way to check that?
I think that's generally a difficult question to check if the Hamiltonian is frustration free if you don't have access to the state. I don't know of a efficient algorithm to determine that.
Actually, even if I have access to the ground state, it may not be very easy.
But if you have access to the ground state, then you can just check if each of these, if it's like positive semi-definite and if each of these annihilate the state, right?
But I'm assuming I have access to the ground state, but I do not know, I only know H, I do not know H tilde.
You only know H and you don't know H tilde?
Yeah.
Oh, but there's a construction. There's a way to get from sum over Hx to sum over H tilde x.
If
Like there's a,
if I know the ground state.
no, you don't need to, so okay. The statement is, okay, I can actually just define this now. Basically this H is integral over some function of Hx of t. So this hx of t is just hx conjugated by e to the iht, where h is a total Hamiltonian. So this is just a construction. You don't, yeah.
Yeah, I think here, suppose I can check. Suppose I have the ground state and I can check H tilde can annihilate the ground state, then it's frustration
Yeah.
free. But if such an H tilde cannot, maybe there's another definition of H tilde that can, right?
Yeah, that's true. So you're asking, that's basically asking if I have a state, does it admit a frustration-free parent Hamiltonian?
Yeah.
Yeah, I don't know of a sharp answer to that. And there are certain things that will rule it out. For example, if the state is a CFT state, then probably no, because the dispersion, the dynamical critical exponent is bounded for frustration-free Hamiltonians. But outside of those ways to rule it out, I'm not sure of a way to determine if there exists a frustration-free parent Hamiltonian.
Thanks. Any other questions? Okay. If not, we thank Carolyn again. So now I will close the Zoom and we can all leave. Thank you.